Hello everyone. In the previous video, we went through what cost functions are. Now we're going to spend a little bit more time understanding the nuances behind cost functions. So cost curves are generally drawn. So we denote costs as they're functions of the prices of the inputs and the amount of output that is being produced. So cost curves are generally drawn under this assumption that the input prices and the technology that is used to produce a certain level of output that is kept constant. Now, so input prices and technology level are assumed to be constant. Now, if any one of these factors change, that's going to shift our cost curves. So in order to understand the mechanics of these changes, let's first look at a few different examples to see how cost functions are actually computed and written down. And we look at that for the case of for fixed proportions for Cobb-Douglas and for CES functions. So let's look at the cost curves under fixed proportions function. So when you have perfectly complementary inputs, the production function takes on this form where Q is minimum of alpha K and beta L. And we know that in such cases, the production is going to happen at, so if you have K and L, the production is going to happen at the vertex. Okay. And at the vertex, we know Q will be set equal to alpha K will be equal to beta L. Now, in for such production functions, we don't need to write down the Lagrangian for fixed proportions case because we know that the consumption can only happen at that one point. There is no point in solving an optimality problem here because we can just identify the point directly from the graph. So we write our cost functions directly. So C of the cost is just Bk plus WL. And from the vertex, so we know that Q needs to be equal to alpha K. So therefore, that gives you that your K should be equal to Q over alpha. And when you set Q equals to beta L, you know that L should be equal to Q over beta. So in this manner, we can identify that level of capital endeavor that will be cost minimizing or optimal in this particular case, given that we are producing some level of output Q. So in this way, you can just go ahead and write down your cost function. Now, whenever there is constant returns to scale, as we saw in the previous video, when you have CRS functions, the total cost functions will be linear lines. They'll have a constant slope. Your AC and MC curves will just become a constant. So when you have CRS in this case, cost of producing Q units of output is just going to be Q times the cost of producing 1 unit of output. So if I scale up production by K units, my costs will also just be, if I scale up production by Q units, my costs also go up by Q units. So therefore, the total cost is just Q times AC, which is equal to Q times MC. These are just mathematical results that you will get. Okay? So that's for fixed proportions. Now, this case is a little bit involved with math. So even if I walk you through these slides slowly, you'll get a good hang of them only when you actually solve the problem. So I'm just going to give you the intuition here. Please work through this on your own. I'll give you the steps and you should be able to do it. So when we have a Cobb-Douglas function of this general form, K power alpha, L power beta, the place where we'll start solving for our cost function, we'll actually just take off from where the cost minimization problem stopped. Remember that the minimum cost happens when the price ratio W over V equals your MPL over MPK. And we know that that result is given by W by V equals beta by alpha times K over L. From that starting point, express any one of your inputs as a function of the other terms in the equation. So here we are choosing to denote K in terms of alpha, beta, W, V, and L. Now, this is an optimal level of K, which has solved our cost minimization problem. Now, all I have to do is take this K and substitute into my production function. So in place of K power alpha, I'm just going to substitute this particular expression. And now I have a resulting expression where the terms are Q, alpha, beta, W, V, and L. From solving this equation, I can write L as a function of all of these other things, alpha, beta, V, and W. So what am I accomplishing by doing this? I've been able to express my labor as exclusively as a function of W, V, and Q. So because our input demands, the amounts of input that we want, we don't have any say on the input prices, and the amount of output to be produced is given to us. So the labor that we'll actually be using will also be a function of these three entities. And that's what we do in this process, where we express L as a function of the other parameters. And once we know what L is, I just have to plug back this L into my expression for K. And when I do that, I'm going to get another expression where K is now a function of W, V, and Q. The algebra may seem a little daunting, but trust me, as long as you pay attention to your alphas and betas and just to your differentiation rules, you'll be fine. So what we've identified now are LC and KC, which are the contingent demand for labor and capital, given W, V, and Q. And once you have L and K, all you have to do is plug that optimal value back into your cost function, and then you have your, then you get a resulting expression where costs are now dependent on V, W, and Q. And that's how you get your cost functions in the Cobb-Douglas case. And we know for a Cobb-Douglas function, this alpha plus beta, it tells us the returns to scale. Now, whenever alpha plus beta is greater than 1, that's when you have increasing returns. Your inputs are more productive. So in such scenarios, your cost function will increase slowly. It will increase at a decreasing rate. So whenever you have IRS, you'll have a concave cost function. And then when the production morphs into a stage where when from IRS we move to CRS, when you have CRS, your cost functions will increase linearly. And once the production crosses that stage into one of decreasing returns to scale, that's when your inputs are not very productive. So you're going to have costs increasing at an increasing rate. So you'll have a convex cost function there. So just by varying the alpha and beta values, you can see the returns to scale and the shape of your cost function also. Now, from the way the cost function is written down, you see that it's a function of Q, V, and W. Particularly W and V are raised to some power, which is definitely possible. So whenever W and V increase, even if one of them increases, then that means your overall cost is going to increase for producing the same level of output. So that's what we say, that if there is an increase in input price, the costs are going to increase. By how much will they increase? That depends on the particular exponents there. So the exponents capture the importance of that input into the production process. So, and this cost function for a Cobb-Douglas case, they are homogeneous of degree 1 in input prices. So if you take your cost function equation, and if you vary V and W by some multiple, say T times V, T times W, if your costs go up by a particular proportion, if your input prices change by a particular proportion, your overall costs will also change by the same proportion. That's what the homogeneity of degree 1 here means. So this is for a Cobb-Douglas case. The next one is for a CES function. Now I'm going to skip through all the math here. Patiently work through it. The process is exactly the same. Now the total cost function in this case is written in this manner. Okay. And the costs are now dependent on some parameter gamma and then rho. So the sigma here is just 1 over 1 minus rho, which is the elasticity of substitution, which we saw in the earlier chapter. The shape of this particular cost function will depend on these parameters, gamma, and also on sigma and rho. Here again, when any inputs price goes up, the overall costs are also going to go up. Okay, so this is just another illustrative case. This function is also homogeneous of degree 1 in input prices V and W. So I'll probably pause this video here and I'll see you in the next one.